Okay, in this lesson we're going to be talking about math of finance. We're going to be applying our exponential functions to money. So let's go over some basic vocab that has to do with finance and banking and interest and whatnot that we're going to be using in this section. Okay, starting off, principal. The principal is the initial amount invested or the initial cost. Okay, so that initial amount that was our a variable in our old exponential functions, that is our p variable. We're going to call it a capital P in our financial interest equations. All right, compound interest is interest that becomes part of the investment that's earned on the interest itself. So, for example, if you have an account that earns interest that's put back into that account, then the next time that it earns interest, it'll kind of be earning interest on top of interest. We've got our annual percentage yield, APY or AYP. It's the percentage rate that you'll be given or you'll be asked to find. The annuity is a sequence of equal periodic investments or payments. And then we've got the present value of that annuity is the net that you've put into it, or it's the amount of a loan. And then the future value is the net returned, including payments and interest, or it's the amount that's still owed on a loan at some future time. Alright, so let's look at our two main formulas that we're going to be using for interest. One type is when we have interest compounded over a certain interval, a certain number of times per year. Okay, so we've got this formula here. We've got A equals capital P times in parentheses 1 plus R over K to the KT power. Alright, so let's break this down. Let's see what each of these pieces is referring to. Alright, so our A value, that's our final amount. Our P value, we just said, is our principal. Our lowercase r, that's our rate, and that's as a decimal. So if you're given a percentage rate as a percent, make sure you convert it to a decimal. Make sure you spell decimal right. Decimal, yep. Alright, and our K value, that is the number of times compounded per year. So for example, if you were given a problem where it was compounded annually, then your K would be 1, since it would compound once a year. If it was compounded quarterly, then your K value would be 4 times per year, 4 quarters in a year. It could be monthly, it could be weekly, it could be daily, so your K value depends on the number of times compounded each year. Okay, so that wouldn't change if it was compounded quarterly over 5 years or 10 years or 100 years. That K value would still be 4. Okay, so that time component is our T value. Okay, and then that K is the same as this K. Okay, so now that we know what each of the variables of our compounding over an interval formula means, let's look at an example. Okay, it says determine how much time is required for an investment to double in value if interest is earned at the rate of 5.75% compounded quarterly. Okay, so given this problem, a couple of keys that we want to pick out from this problem. The first one I see is it says compounded quarterly. Okay, so that tells me that I want to use this formula here. All right, so how it's compounded, how that interest is compounded, lets us know what formula we want to use. Okay, they tell us that our interest rate is 5.75%. That's important. They also ask us to find how much time. So we're going to be looking to solve for t. How much time is required for that investment to double? So let's set up our equation. Okay, so let's start off with our same equation we have up here. A equals capital P times 1 plus R over K to the KT power. And let's plug in what we know. If we're looking for our investment to double, then even though we don't know what our P is, our principal, so they don't give us how much we initially invested, but if our initial investment was P, then twice that is just 2P. So when we solve for T, this is actually going to work for any principal that was put in. Okay, we got P times 1 plus, and then our rate is 5.75. We want to make that a decimal, so move that decimal to the left 2 units. So we've got 0.0575. Don't forget that 0 is a placeholder, over our K value. So since we're compounding quarterly, our K value is 4. All of that is raised to the 4t power. And we're looking to solve for t. Okay, so the first thing I want to do is I want to try to get this whole power here by itself, since my unknown variable is in my exponent. So I want to divide both sides by p. Okay, so that's going to p over p is 1. P over P is 1. So what that really does, I'm going to come over here, is that gives us 2 equals, in parentheses, and I might go ahead and put this in my calculator and get 1.014375. No rounding until the very end, so even though that's got 6 decimals, go ahead and keep them. And then that raised to the 4t. Alright, let's see, our variables in our exponent. So we can convert to log form. So we've got log, and our base is 1.014375 of 2 equals, remember our log always equals our exponent, so equals 4t. We want that t by itself, so divide both sides by 4. Our time is log base 1.014375 of 2 over 4. So putting that in your calculator, we get our time is approximately 12.141, and our units are years. Okay, so let's look at our other formula that we kind of encroached on over here. All right, so this formula is useful when we have interest that compounds continuously. Okay, so continuously compounding interest doesn't just compound once a month or 4 times a year or once a week or once a day. It theoretically compounds continuously. So our different formula, we've got what looks like a much simpler formula, A equals P e to the RT, or we'll call it our PERT formula. Okay, where our A is still our final amount, our P is still our principal, that E, that's our constant E, so that's not a variable. Our rate, our R again is our rate as a decimal. Okay, we don't have to worry about a K because we're not compounding over an interval. And our T again is our time. So let's look at an example for this one. Find the value of an investment with a principal of $3,350 at 6.2% compounded continuously. That tells us what formula we're going to use for 8 years. Alright, so let's start with our formula. We've got A equals capital P to the E times E to the RT. Let's plug in what we know. We're directly told our principal, so let's plug that in for P. E, and our rate as a decimal, again, move that decimal place over 2 to the left. We've got 0.062, and our time is 8 years. Okay, and we're looking for our value, our final amount. So you can plug all that into your calculator. We don't have any missing variables. And rounding to the nearest penny, we should get $5,501.17. Okay. Now, there are times when the problem that we're going to be given is kind of beyond either of those two formulas. Okay, so we can use for certain problems the finance app on our calculator. So if you got your 83 or your 84, it should be preloaded with this finance app if you press the apps button, which is right next to the math button. And if a lot of times it's the only app that shows up, it's called finance. If not, you might need a cursor down and find finance. Then you press enter, and then the first option should say TVM solver. So if you press enter one more time, then you should get a screen that looks similar to this one shown here. So let's go over what all these variables mean, because we've got several here that are new to us. Okay, so the N value, that capital N value, is the number of compounding periods. And I might enter a little note up here saying that is the total number of compounding periods. All right, the I percentage is the interest percentage rate, or the annual percentage rate. PV is the present value of the account or investment. PMT is the payment amount if we're making payments over a certain interval. FV is the future value. P over Y is payments per year, and C over Y is compounding periods per year. For our purposes, CY and PY will be the same. And unless we're told otherwise, we're going to leave our payments at the end, as it should already be highlighted. We'll look at an example in just a minute of the only type of a problem where we'll switch that to the beginning. Okay, so let's look at an example. We'll Let's look at example number 6. Okay, so Sal opened a retirement account and pays $50 at the end of each quarter, which is 4 times a year, into it. The account earns 6.12% annual interest. Sal plans to retire in 15 years. How much money will be in his account at that time? Okay, Sal really wants to know. He wants to know if he's going to be well off or not. So let's help out Sal. Let's list our variables here. So I've got kind of a copy of the calculator screen, and I'm just going to plug them in as we read through the problem again and see where they go and see what we need to solve for. Okay, so first off, he's paying $50 in at the end of each quarter. So that means that the payment is not going to be 0, but it's going to be 50. So maybe, let's see, you're gonna cursor down on your calculator, and you're gonna make that payment 50. Okay, since it happens 4 times per year, let's make our payment per year. Let's maybe scratch through that. Can I get a? Oh yeah, let's get rid of that. All right, much better. So our payments per year 4, and then let's copy that to our compounding per year. Okay, the account earns 6.12 interest. Now, be careful. The interest that you put into the finance app is a straight up interest rate, not as a decimal per se. So we want to put in that exact interest rate. Okay, Sal plans to retire in 15 years. So in our N value, if he's going to retire in 15 years, then it's going to compound 15 years at 4 times per year. So if we do 15 times 4, then that should give us 60 compounding periods. Okay, so you can put in 15 times 4, or you can put in 60. Your calculator is cool with either one. Okay, what else? Let's see. His present value is going to be 0, so he's not starting off with any money in his account, and we're looking for that future value. We're looking for how much it is. So after you filled in all of these variables, if you cursor down to FV, and then if you press alpha, and then you press the enter key, so alpha, enter, and then it should fill in a value in for that future value. And in this case, it should give you a negative 4859.241063. Okay, so we can interpret that as meaning that this account is going to pay out $4,859 and to the nearest penny 24 cents. Okay, so if we keep these as positive numbers, so we're paying in $50, then it pays out. That's why that's negative. It pays out $4,859.24. So Sal will have just shy of $5,000 on his retirement. He might want to put a little bit more money in his account. Alright, example number 7. Kim wants to buy a used car for $9,000. The bank offers her a 4-year loan with an APR of 7.95%. What will Kim's monthly car payment be? Assume she makes her payment on the 1st of each month. Okay, so this last piece here, since we're making our payment at the beginning of the payment period, then we're actually going to change that to begin. Okay, this is one of the few times we're going to change that. And let's see, I'm going to go ahead and get rid of some of these so it's more legible. Alright, now let's see what we got to work with. Okay, she wants to buy a used car for $9,000. So if she's taking out a loan, then the present value of that loan is going to be $9,000. And since that's not her money, it's actually the bank's money, so we're going to make that a negative, so that when we find her payment, that's going to be the positive that she's going to be paying into it. Okay, the interest rate is 7.95%, so again, put that in as a percentage. It's a 4-year loan. She's making monthly payments. So our end value is 12 times, so 4 times 12 is 48. We are looking for the payment. That's our unknown. So we're going to leave that blank now, or just leave whatever other values in it. The future value, we want her to totally pay off that loan. So that loan should go all the way down to 0 when she's done paying it off. And if she's paying it off monthly payments, they're going to be 12 per year. Same thing for our compounding. So now we've got all of our variables except for our payment. So cursor down and highlight payment, press alpha enter, and it should give you 218.06 and some change. We just want it to the nearest penny. So her monthly payment should be $218.06. It's not so bad of a monthly payment. Okay, on the next sheet, here's 2 more examples. If you'll take the time to work these 2 out, filling in each of the variables that you'll put in your calculator and calculating the appropriate value. And tomorrow in class, we'll go over these and we'll work out some other examples using exponentials and finance.